Hello class, this is Ms. Riggins with today's video on section 4.1, using the first and second derivative. As you're watching the video, please remember to take notes, writing down any important information, equations, statements, or formulas. Feel free to pause, rewind, or even replay the video as often as you need. And don't forget at the end of watching the video to write down your summary about what happened in the video in your notes, as well as submit the summary as well as an top question via the online WISC. All right, let's begin with class. We've been working with first and second derivatives, computing first and second derivatives, but now we're going to see how we use the first and second derivative. And just as a refresher, before we start talking about the first derivative and how we use it, let's refresh what we know about what the first derivative tells us about the function. So if the first derivative is positive on an interval, then the original function is increasing on that interval. And if the first derivative is negative on that interval, then the original function is decreasing on that interval. So in order to determine which intervals are which, we need to specify where the first derivative is 0. So let's just say we have some function where the first derivative is defined and it's 0 at, let's say, 2 points, x equals -3 and x equals 7. So in other words, now we have a few intervals that we can use to describe what's going on with this function. One interval is when all the x values are less than -3. Another interval is when all the x values are greater than 7. And the third interval is the interval when the x values are in between 3 and 7. So in order to determine whether the function is increasing or decreasing on those three intervals, what we do is we pick a point in each of the intervals and test and plug it into the first derivative and see whether or not it's positive or negative. So let's say, for example, we pick a point from -infinity to 3, and we call that point B and plug it into the first derivative. And let's say we get something that is less than 0, just as an example. So that would tell us something about that interval. And we pick a point C, which is in the interval -3 to 7. And if we test the first derivative, sorry, that should be first derivative, that would be happy. At that point, and we get something that is, actually, let's make this greater than 0. And let's make this negative. And we'll do an actual example at the end of the video if you want to see how it's done. And we see that we get that something less than 0. And let's see for a value d, which is in the interval 7 to infinity, if we plug that into the first derivative, we get a value that's greater than 0. Then what does that tell us? It tells us several things. It tells us that on this interval, since the first derivative is positive, that the function is increasing on that interval. And over here, since we got that the first derivative was negative on the interval from -3 to 7, that would mean that the function is decreasing on that interval. And over here, since we found that the first derivative d was positive, then that lets us know that the original function is increasing on that interval. And so that's what we used to find out information about the original function. How do we use the second derivative? Well, if you recall, the second derivative will tell us about the concavity of the original graph on that interval. So if the second derivative was positive on an interval, then that would mean that the graph was concave up. And if the second derivative was negative on that interval, that would mean the graph of the original function is concave down. So we would also need to find a value or any values for which the second derivative is 0 and plug that in. And if we got that the second derivative for a point in one of the intervals was negative, then we would say that the graph is concave down. And if we plugged a point in the interval into f prime at that point, and we got that as positive, then the graph would be concave up. So that's what we did in the past. And so let's see how that applies to what we're doing today. Now, before we start that, we need to define some things. Extrema. Extrema is basically a minimum and a maximum. Okay, and we call it local if it's really close together on a small interval, or not even a small interval, but just in an interval. We call it a local minimum, or if it's a local maximum. And the definition for a local minimum is You have a local minimum at P if f of P is less than all, f or equal to f of x for all x close to P. Hence the word local. Okay. And it's a local maximum if f of P is greater than or equal to all f of x for all all x that are close to P. So that's what makes it a local maximum. And we call these local extrema instead of saying local minimum and local maximum. Okay, so how do we go about finding a local minimum and a local maximum? Well, we go about finding those values using by determining a critical point. And some of you may be saying, what is a critical point? And this is a new terminology, so make sure you write this down and learn it. A critical point is a point P or x value P in the domain where the first derivative of that point P is either 0 or undefined. Then it's called a critical point. No, some of you may be saying, well, where's the y coordinate? So this is tricky. They call it P because it's a point in the domain, an x value in the domain, but it's also a critical point is the point P, comma, f of P. Okay, the value of the function is called a critical value. Okay, so that's just new terminology. But if you say it has a critical point at P, then that's sufficient as well. Okay, and so we have a theorem, which is Theorem 4.1, which says that if f is defined on an interval and has a local maximum or minimum at that point, then, which is not an endpoint of the interval, then f is differentiable. Then if f is differentiable at x equals a, then f prime of a is equal to 0. Thus a is a critical point. All that means is that if you have a function that's defined on an interval and has a local maximum or minimum at some point in that interval, then if the function is differentiable at that point, then that must mean that the first derivative of it at that point is 0. Okay, and then that point A is a critical point. Okay, and we have a theorem to explain why that's the case. A proof to explain. So if the function is differentiable at x equals a, then that must mean that this exists. And if this exists, then that must mean as h approaches 0 from the left side and as h approaches right side from the right side, that they are equal. Okay, well, let's take a look at this. If f is a local maximum or minimum, they didn't specify, as long as it's either or, then either f of a plus h is less than f of a for a local maximum, which means this difference is less than or equal to 0, or if it's a minimum, that f prime of f of h, a plus h is greater than or equal to f of a, which means that this answer, this difference is positive. Well, why is that important? Because if we're approaching this value from the left side, it means that either that h is negative, and if we're approaching h from the right side of 0, it means that h is positive. Okay, so that must mean that when you have x, and this is for the local maximum, that the local maximum ratio would imply that this value is less than or equal to 0, and that this value is greater than or equal to 0. And if it's a local minimum, that this would imply that this ratio is greater than or equal to 0, and this ratio is less than or equal to 0. Well, since they both can't be less than or equal to 0 and greater than or equal to 0 without being 0, then that must mean that the first derivative is equal to 0. So the proof is basically that if you have a minimum or maximum, it has to occur at a critical point, and a critical point is when the first derivative is either 0 or undefined. Okay, so why did I go through the time to take that? Because it's good for you to understand, but let's go and take a look at a theorem. First derivative test, which we've kind of already done. All you have to do is find the points for which the first derivative is 0, i.e. find all the critical points, so whether it's 0 or undefined, so that's important to note. And then test the first derivative at a point in each of the intervals that it produces. And if the first derivative is negative on the interval, then that must mean the whole function is decreasing on the interval and vice versa. And if it's positive, then that must mean that it's the function is increasing on the interval. But why is that important? Well, if a function is going from decreasing to increasing, which means that that p would be a local minimum. And if the function is going from increasing to decreasing, then that p is a local maximum. So not all critical points are going to be minimums or local minimums or maximums. But if you're going to have a local minimum or maximum on that interval, it would occur at a critical point. And in order to determine if it's a minimum or a maximum or neither, we have to test the first derivative at a point on the interval surrounding that. So for example, if I get minus and minus, which means that this p, even though it's still a critical point, it's not a local minimum because it's increasing on those same intervals. Second derivative test, I don't like to use, because why would you use the second derivative test if you have the first derivative test? But anyway, the second derivative test says if you don't want to test the value on the interval into f prime, just test the value on f double prime. And if you get that the first derivative is 0 at that point, but the second derivative at that critical point is greater than 0, then it's going to be a local maximum, and that's because if you have a concave up situation, that must mean that p is a local minimum. And the same for if you test the first derivative at that point and you get that the second derivative at that point is less than 0, then f would have to be a maximum, because you would have a concave down situation, and the first derivative at that point being 0 means that it is a local maximum. And if you get 0 for the first derivative test and the second derivative test at a particular point, you know nothing. All right, so we're going to talk about very quickly an inflection point. An inflection point is a point where the graph changes concavity. And to determine if a point is an inflection point, we have to find where the second derivative is 0 or undefined, and that's important to note. And if it is a second derivative is 0 or undefined at a point, then that point p is a possible inflection point. Okay? And in order to test whether it's an inflection point, we have to test to see whether the sign changes on the left interval and the right interval of p, similar to a local minimum or maximum. And if the sign changes, then yes, then you have an inflection point at that point. So let's take a look at an example. Here we have a function, a polynomial function. We take the first derivative of it, and we get this. And I like to factor it so I can easily see my 0. So I have a 0, as you can see, at, oh gosh, that's not right. Okay, sorry, I had to fix it. It was a typo. So I have a 0 at 3 and a negative 2, as you can see here. So when I pick a value to the left of negative 2, so let's say negative 4. Negative 4 minus 3 is a negative 7. Negative 4 plus 2 is a negative 2. Negative times a negative is a positive. I pick a point in this interval between negative 2 and 3. 0 is always the easiest. So I pick 0 minus 3 and 0 plus 2. I would get a negative 6. So my answer, that means the first derivative is negative on that interval. And I pick a point greater than 3. Let's say 4. 4 minus 3 is 1. 4 plus 2 is 6. I get a positive answer. So that must mean the original function is increasing on that interval because the first derivative is increasing. And I draw little arrows to help me out with that. Then I do the second derivative, take the second derivative of the function, and I get 2x minus 1, or 2 times x minus 1/2. Now, if I didn't want to do this test with a plus, negative, plus, I can plug in negative 2 to this and see, oh, well, I get a negative number, which means the graph is concave down. So then, therefore, I must have a maximum at this point. And we could see that as well, too. I like to put maximum, max, because the sign changes from, so minimum. So I could also use a second derivative test as well. It's up to you. It will work either which way. So then I test for concavity, and so the value that makes the second derivative 0 is 1/2. So I test a value to the left of it, 0. 0 minus 1/2, so 2 times negative 1/2 is a negative number. Test a value to the right of 1/2, 1. 1 minus 1/2 is 1/2 times 2 is a positive number. So I draw concave down and concave up. And since the concavity changes, then that must mean I have an inflection point at x equals 1/2. So inflection point. Okay, and so that's how we use the first and second derivative. Sorry, this video ran low, but I wanted to show you the proof. All right, that's it.